This session is fairly easy. I don't think you'll have much problem with it. Probably junior level, and it'll probably be fairly quick. As you can see, so we're into a new section now. 3 sections in this chapter, chapter 3. Section 2, variants of Turing machines. In other words, variations. You're modifying the design, the basic definition, if you like, of the Turing machine somewhat. Variations, or variants, A-N-T-S. Okay. Now there are lots of variants of Turing machines that you can imagine that have been thought of in the past. Some obvious ones, you might change the number of tapes, have more than one. You might have a machine with K tapes, right? So that's one that we'll talk about in this section of the book, right? Another variant is to have a Turing machine, which so far in our discussion of the Turing machine has implicitly, it's been implied, unconscious almost, that it's deterministic, right? Because we've always had just one next state. Right? When we went from Qi to Qj, there's only one Qj. But non-determinism, by definition, means the possibility of more than one next state. And when there is more than one next state, well, then you split. Right? You make a copy of the machine, the Turing machine, and one copy will go down one branch of the, what do you call it, the configuration tree, the history of the configuration. So one branch of the Turing machine will go down, one copy of the machine will go down one branch, and another one will go down another branch, and so on, at each split. Right? So non-deterministic, that's another possibility, another variant. So multiple tapes, K-tape machine, and non-deterministic Turing machine. So we'll deal with both of these 2 variants in this section, and there are others, but just give a taste. Okay, well, a bit more. We'll go into some detail. Now, as I was saying in the previous session, one of the main ideas of this section is that these variants of the Turing machine, they all have the same power, meaning that is, they recognize the same class of languages, the same set of languages. That's how you define power. If one machine can recognize a larger class of languages than another, well, it has more power by definition. Okay. Now, so what we're going to introduce, these 2 variants at least, so multi-tape and non-deterministic Turing machine, and we will prove, theorems, we will prove that they are equivalent in their power. In other words, they recognize the same languages. So 2 machines are equivalent. That means they would recognize the same. Well, how can I put this? You're given a language, then if 2 machines both recognize that language, then those 2 machines are equivalent, at least with respect to that language. Maybe some other language, a different question, I guess. But anyway, right. Now another concept, the idea of robustness. Robust, what does that usually mean? It usually means sort of strong, resistant against something. Like quantum computers are not robust. They are highly sensitive, fragile to noise, like external unwanted noise. That noise, those external influences, electromagnetic fields, other atoms, whatever, they destroy the quantum state. So they need to be made robust. In this case, robustness in this context means that you can modify the Turing machine design somewhat, and it still functions like a Turing machine. It's still equivalent. The modified version, the variant of the Turing machine, is equivalent to the original design. Okay, so the original design, in a sense, is robust in the sense of you can make variants of it, and it still functions like the original Turing machine. Okay? So the original Turing machine design is robust against changes, if you like. So it still functions as a Turing machine, even with its variants, ANTS, the noun. Okay, so that's what that's saying. Now finite automata and PDAs, they're somewhat robust. We haven't really talked about that. But the Turing machine robustness, the level of its robustness, it's extraordinary. Now, it's a strong word in English, right? It's extraordinary. Meaning it surprises by just how robust it is. Even, it's a huge step to go from, for example, the simple Turing machine design that we've been talking about to, say, today's supercomputers. But even with that huge variation, right, the power of that supercomputer, today's supercomputers, is still equivalent to the original Turing machine design. Right? It may be hugely more efficient, but in terms of power, in the sense, can it recognize a greater set of languages, greater class of languages? Nope, still equivalent. And all these theorems showing that this variant and that variant, they're all equivalent to the original Turing machine design. Proving equivalence is one of the major components of computability theory and complexity theory and so on. So the level of robustness of the Turing machine is extraordinary. Right? That's why the Turing machine concept has stuck around for so long. It's potent. It's very powerful. Okay? So if you can prove theorems about the Turing machine, given the equivalence with the Turing machine and today's real-world computers, given the equivalence, so if you can prove things cannot be done with Turing machines, given the equivalence, therefore you know that today's machines cannot do the same task, right? That's really useful to know. So people speculate about the concept of what they call super Turing machines, machines that can do more than what Turing machines can do. And interesting concept. One of my dreams is to go beyond what quantum computing can do to outperform the 2 to the power n is the number of quantum bits, qubits in your quantum register. My dream is to find, in a sense, super quantum computing. But I haven't really sat down and thought about it with such a super quantum computer. Would it still be equivalent to a Turing machine? Maybe. It's a really potent concept, right? So robustness. Okay. Now here's an example of the robustness of a Turing machine. We change, we vary. We have a variant of the Turing machine, basic design, and we change it a little bit. And you can just sort of see here from the transition function, and all that up to here is all the same, all familiar, but this is new. And you can probably guess what S would mean. S for stationary, or S for stay put. In other words, you don't move left or right, you don't move at all, you just stay there, right? Stay, S for whatever, stay, stationary, stay put. Okay? So you change the state, you write on the square, and then instead of moving left or right, you don't move at all, you just stay on the square. So effectively you've just overwritten the symbol on the tape, but you haven't moved. Okay? Now, with a Turing machine that had that variant, that variant Turing machine, is it more powerful? Could it recognize a larger class of languages? Well, we can show pretty quickly, actually, that this variant of the Turing machine is actually equivalent to the standard model of the Turing machine. And how do you do that? Well, so if you have a Turing machine with this extra feature, that you don't move, is this modifier, this variant of a Turing machine, is it more powerful? Can it detect, can it recognize a larger class of languages? The answer is no. Okay. Why? Well, because we can convert this modifier, this variant with this S here, we can convert it into a conventional Turing machine by how to do that? Well, you replace each stay put transition. So any transition that has an S here, so you have new state, symbol to be written, and an S. So whenever you have that transition, then you can replace it by two conventional transitions from your transitions from your conventional Turing machine. And let me try and illustrate it. Okay, say this is the tape on your machine, your variant, the one that has the S, the stay put feature. Okay, so here's the head, and let's say my knuckle here. Let's say that had character A, the symbol A on the square. Okay, and then with your, I'll call it the S variant, the variant of the Turing machine that has this stay put feature, doesn't move. Okay, and say you now write a B here, and you just stay there. Okay, so the symbol here, my knuckle here, the square on the tape, it was A, and then it got overwritten, and now it's B. Okay, and the tape, the header did not move. It's still over, but now it's over the B. That was an A. Okay, that's what you can do with the S Turing machine. Okay, now the conventional Turing machine. Well, you can do the same, but you now you need two transitions, two steps. Well, you could do something like this. Now we have to end up with the same, right? We have to end up